provide several examples. Okay, so we first define a set of all real polynomials of degree less than or equal to 3. Alright, so you can see that they are in general 4 terms: constant term, linear term, square term, and the cubic term in general. Right, so the vector addition. The vector addition actually is from P3 from a pair of real polynomials of degree less than 3 to P3. And the rule here is that if we have A0 in 1x, right? So if we have the first polynomial and the second polynomial, right? Okay, then after the vector addition, this is just the addition of 2 polynomials, and it becomes to okay, so that we add 2 polynomials of degree less than or equal to 3, and we end up with a polynomial of degree less than or equal to 3 here. And the coefficients for each term are just the addition of the coefficients of the 2 polynomials. Okay. So vector addition in this set is just polynomial additions, right? How about scalar multiplication? This is R, goes to P3 and goes to P3. So that if we have a scalar alpha, a real number here, and a polynomial, right? And the value for this pair after the operation of scalar multiplication becomes to alpha is 0. I think I don't need the parentheses. Okay. So it's alpha is 0 plus alpha is 1x plus alpha is 2x plus alpha is 3 square and 2. Right. Oh, I'm sorry. I must be busy. Okay, so this is just a polynomial of degree less than 3. Okay, so for the operation, we know that this is indeed vector addition is a mapping, is a function from this Cartesian product 3. And the scalar multiplication is a mapping from the Cartesian product of the set of all real numbers and the set of all real polynomials less than degree less than equal to 3, and map to PC. Okay. So vector addition and scalar multiplication are well defined. And now, so we can check. And then check that all 7 axioms. Okay? For a vector space are fulfilled. For example, the 0 polynomial is just the 0, right? For the vector addition. And for each polynomial, we have additive inverse, just the negative polynomial, right? To add the original polynomial to get the 0 polynomial, etc. That is easy because you are familiar with the algebraic manipulations of polynomials. That P3 is a vector space. Okay. I just, because I want to set a term, so you can check, but I ask you to check it. And a remark here, so just several remarks here. From this example, we can extend the example to, so the P sub n, the set of all real polynomials of degree less than or equal to 2, and okay. So this one is also a vector space. Okay. And more generally, P defined to be the set of all polynomials okay, all polynomials. There is no limitation on the degree of polynomial, just any polynomial. Okay, it's also a vector space. All right, and to express the vector addition on P, all right, and we have to be careful. So here, because that if we add two polynomials with different degree, it's possible. Okay? So that I will write. All right, polynomial by this summation notation. Okay, and all right. So this is a polynomial of degree less than or equal to n. This is a polynomial of degree less than or equal to n. All right, and the summation becomes to say all right. So the degree will be the maxima of nm, and this is ak plus bk. Right, with the with AI equal to 0 for all I greater than n, and the B I equal to k. Right. So this is the way to do that. And the scalar multiplication. So here is alpha, summation, I from 0 to n. AI is I. We'll move to summation, alpha AI. Alright, so you see that vector addition and scalar multiplication are well defined on the set of all polynomials. Okay, so that is familiar. This example it is familiar with it. Now the second example will be a little bit unfamiliar. C parenthesis and interval. What's interval? So what is that? This is the set of all real valued continuous function. All right, continuous functions from -1 to 1. Okay, so this is the f to R such that f is continuous. Okay, so by notation, so C parenthesis, the interval from -1 to 1 is the set of all functions from this first interval to the set of all real numbers because they are real valued. And we require that C means that these functions are continuous. All right, so I hope you still remember the continuity of real value functions that we learned from calculus. Okay, and so the vector addition for the vector addition that given to continuous functions on -1 and 1, that the sum, the sum will be FP plus T. Okay, this is you know. And for scalar multiplication, for a pair with a scalar alpha and a function ft will make to alpha f of t. So it's just a scalar times with the function ft. Alright, so you see that this is just the ordinary operations on functions, on real value functions. Okay, you have learned in calculus. So yeah. And the reason why the sum is continuous has been proved in calculus. Because in calculus, I think you already have a theorem that says that if f and g are continuous function, then their sum is also a continuous function. Right? I think you can go back home and check your calculus textbook. There must be a theorem about this fact. Okay? So this is not trivial. You know, you have to prove that. But fortunately, calculus provide the proof. Secondly, given a scalar, a real number, and a function, this product is also a continuous function when f of t is continuous. So you need to prove, but also again, it is given. So I have to give a remark that So I have to give the mark in calculus. Okay, the sum of two continuous functions ft and the gt is also continuous. Okay, so I read the fact here. Similarly, alpha times ft is continuous if f of t is continuous. So that's the vector addition plus and the scalar multiplication are well defined. All right, so this tells you that the vector addition and scalar multiplication, once given on a certain set, you have to verify that they are well defined. Means that the result should be also in the set. Okay? Should be in the set. And also the schema of the result of the scalar multiplication must be also in the set. And once we know that we have we can check that all 7 axioms are fulfilled, i.e. C minus 1, 1 is a vector space. Okay, so it's a vector space. But now the concept of vector space can be applied to functions. All the set of all continuous functions defined on the first interval from -1 to 1. Okay? Alright. Again, this definition can be extended, so I give a remark. So let I be an interval. Okay? On the real line, i.e. I could be the whole real line from minus infinity to infinity, or a cross half ray right, to the left, open half ray to the left, open half ray to the right, cross half ray to the right, and cross interval half close, half open. And finally the closed interval. So they are basically 1, 2, 3, 4, 8 types of intervals. Now let Ci be the set of all real values continuous functions. Next one. Okay, the function is a little bit longer, so then this shorthand notation. So I use fx, means functions. A little bit lazy, but hope you accept it. Okay, so in notation, so this is actually f from I to R, such that f is continuous. Then Ci is a vector space. Okay, with one vector addition. Ci cross Ci to Ci, and here f of t, goes to the sum. And the sum is also continuous if ft and gt are continuous by calculus. Okay, calculus again. No matter which kind of interval you are talking about. Okay. I think most of the elementary calculus prove respect for derivative functions on a cross interval, but actually the same proof can apply to any kind of intervals like that. Okay. So I just make an assertion here that if f and g are continuous real value functions, then their sum is also continuous. And the second scalar multiplication R goes to Ci. So alpha f of t goes to alpha f of t. And note that the zero vector in Ci is just the zero function defined I. Zero function means that the function is value all zero. All right. And the third example is defined to be the set of all given sequence. Right? And it's denoted as so it's all used. are infinity to denote. So that is the set of all infinite real sequences. Okay? And each sequence may converge or may not converge. Fine. Just write down everything here. Okay. So each vector, each element in V is just an infinite sequence of real numbers. And the study of infinite sequence is also a major target in calculus, right? But you usually focus on the convergence of an infinite sequence. Sometimes you consider the absolute convergence of a sequence, right? In calculus, mathematicians developed several theorems for the convergence of infinite sequences. Alright, so yeah. So for now, forget about the convergence. Okay, just infinite sequence. So now we can define vector addition of two infinite sequences in the way we have done in calculus. So right, and for that, so we have say the usual way would be usually we use an infinite sum to represent an infinite sequence, but that will have a danger, that because every time we write a sum, usually we can see the convergence or divergence of that. So it's a little bit dangerous. So well, right? So I use that. Right? A formal representation of infinite sequence here, and so that it comes to x1 plus y1, x2 plus y2, etc. Okay. So the sum of these two infinite sequences is actually an infinite sequence such that the components are sums of the corresponding components. Okay. So that's the situation. And scalar multiplication will be alpha, and x1, x2, goes to alpha x1, alpha x2, Right. So these operations are the same. These two are the same as we did in calculus. All right, so we can check, again, we can check. All 7 axioms are fulfilled. So that infinity is a vector space. Okay? So infinity is a vector space. And over R. Okay, overall, I will gradually, and from time to time, to write over something to say that the scalars are real scalars. Because later on, we will extend the concept, or the concept for vector spaces over complex numbers. So the scalars become to be complex numbers. Yeah. But up to now, we still consider vector spaces over real number. Okay, it means that the scalars are real numbers. So over R, just give you this concept. Now, the zero vector in R, infinity, is the zero sequence. 0, 0, 0, okay? Zero sequence. And remark, the operation for x1, x2, y1, y2, right? Because class is operation, but the definition is just making a function from the set of all pairs go to an element in infinity. So that this is actually sometimes we write to be, okay, so we put plus in the middle. Okay? So here. And the scalar multiplication, alpha, right? It's just what just right. Okay. So instead of use the notation of functions, we usually put the function as an operator. So an operator we put in the middle, because that is binary operator. Why we call binary operator? Because that we are dealing with pairs. So we have binary operator. Okay? So vector addition is a binary operators, and usually we put binary operator in the middle of to operate. This operator and this is to operate. Remember, you know the operator when you learn programming language, right? I'm not sure. Were you learning the C language in the first year? I'm not so sure. Probably because I taught programming language many years ago. Right, but it's good you learn C or even Python. You should know operator and operate, right? So operator operate on operates. So a binary operator has to operate, right? And a pair is to give you places to put the two operations. Okay. So this is vector addition. All right, so now we have three examples. And the first one. We'll talk about the one, R. Right? Defined to be all real value functions on the real line, such that the absolute value of the function is integrable, means that we can integrate this absolute value of the, and then the result finite. Okay, so verbally we can describe that this is the state of all real valued integrable functions on R. Okay, so the domain is the set of all real numbers R, and the codomain is also R. Okay, so it's a function from R to R, but not just a function. This function, all right, can be integrated. Okay, so it's integrable, right? And that this improper integral, right, is finite. And in your calculus, that in the first course of calculus, that integrability is really the Riemann integrability. So that you are familiar with the definition of the integrability, means by Riemann, right? So it's called Riemann integrable. Right? But sometimes later you may encounter some difficulty, especially if you are, as most of you are electrical engineering students. You will deal with function with jump, means that not every function you consider as continuous. For example, the step function. Okay, in your circuit theory, you should deal with discontinuous function, but not very bad. The discontinuity just occurs from time to time, means that discrete time only, right? Not very complicated. And this kind of functions can be also deal with by using so-called piecewise integrability. That's where if we can forget the discontinuity, and for each segment that the function is continuous, you still can define Riemann integral. Right? So the Riemann theory of integration is still workable most of the time. Okay? And then when you go deeper, when you encounter a little bit more complicated functions, then you may need to a more general idea of integrability, such as the back integrability. Okay, and then you have to study advanced calculus to know the concept of the back integrability. Right. So for here, I just say integrable means that you may, it's up to your experience, right? You may just consider Riemann integrable functions. Okay, Riemann integral function. Not every continuous function are Riemann integrable because you are considering improper integral. You integral over the whole real line. For example, a constant function, for example, a constant function with value 1 is not integrable. Why? Because when you integral a constant 1, if the integral is 1, the value is infinite. It's not finite. Okay? So even a continuous function, even it's continuous over the whole real line, you can't integrate it. Why? Because it approaches to infinity. Okay, so this set of all functions is not trivial. See, okay, but the real world functions, especially in engineering, you can't have a function. We deal with functions as signals, as time signals, and so signals come from some time, not forever, not from. Because the universe, the whole universe exists in a finite number of times, right? by theory, by physics, right? We have a Big Bang, and then the universe turns out appears suddenly, and it seems like the whole universe will collapse back to a singularity point, and so that is the end of the whole universe. All right, this is just up to now a Big Bang theory, and so that we can't have a function or a time function from infinity to infinity, right? In reality, I mean in the physical world. So basically, such a function is very realistic, right? Because in practical world, that most of the functions satisfy this property. Okay, satisfy this property, and whenever we work on this set, we still can get rich results, and can be used to solve our everyday life problems, even in flights, or vehicle, or many engineering problems, science problems, even in economic systems. All right, so integrability is very important here. But when we put the restriction here, we have to be careful. All right, so here is an example. Example of a linear function. A linear function. Okay, then if we integrate, all right, we are doing. So this is 2. All right, and it's 2 times 2t squared. What has happened? This has become 2 infinity. Okay. So f of t equal to t is not integrable, even though it is continuous. And f of t not in the 1. Okay, so it's not in here. So for this example, you may be disappointed. Why? Because you say, well, this is a very common function encounter, right, in mathematics. All right, but another example. How about an exponential function? All right. Quite often, in practical situations, that you will exponential decay. It's continuous, of course, so that there's no problem to do the integration. Okay. Right. So this is 2. So this is 2. And it's finite. Okay, so that f of t equal to e to the minus t in 1R. Okay, now we define vector addition. Right. 1R goes to the 1R goes to the 1R. Right. So we have ft dt. Right. So given 2 real valued integrable functions. And the sum, we have to prove that the sum, their sum, is also integrable. So the question, so now we have question. It's ft plus gt L1R if ft gt L1R. So that is the natural question you should ask. Alright, so the proof is that okay, so you should deal with the absolute value of the sum here. Absolute value of the sum. But we know the absolute value of sum is less than or equal to the sum of their absolute values. Okay? So we first have an inequality. And by the linearity of the integral, because we prove linearity of integral need to be proved, but we have done that in calculus. So we apply that. So this becomes 2 plus. Okay. So when we integrate the sum of two functions, this becomes 2. The sum of their integral. And it is true because that these two are finite. Because we know f and g in L1. F and g in L1 means that their integral is finite. So we have that. Okay. So we justify that this sum is indeed in L1. Okay. The second, scalar multiplication. Goes to the 1R. So that is alpha ft goes to alpha ft. So once again, question. This alpha ft in the 1R is f of t is in the 1R. Okay. Alright, so we have to check alpha f of t. So this comes to, so the absolute value of our times ft is equal to the absolute value of alpha times absolute value of ft. And again, by linearity of integral, we have that. And this is infinite, so it's this is finite, so the product is finite. Okay. Okay, and finally, you can check, or we work together, so we can check that all 7 accents are filled. Alright, so L1R is a vector space. over R. And this is the first example. Now the fifth one. I take this example from our previous discussion. So let A be an M times N matrix. Okay, over R means that the entries of this matrix are all real numbers. Now the kernel of A, denoted by KERA, is a vector space. Okay, so we have to verify this. So first of all, vector addition from kernel A to kernel A, so that we have x, y goes to x plus y. Now, how do you know if I take two vectors from the kernel of A and their sum is also in the kernel? That is not trivial, so you have to prove, right? So the question is x plus y in kernel A if x, y in kernel A. Alright, so you have to prove that. The reason is that when you check the multiplication of A with the sum of x and y, and by linearity of matrix multiplication, we have this one. And because x is in kernel A, y is in kernel A, so AX is 0 plus 0, okay? So 0 plus 0 is 0. So that x plus y is in the kernel of A if x, y is in kernel of A. Okay, so we have done. This is well defined. Okay, so you have to value that. Alright. The second thing is about define scalar multiplication. As usual, so you have alpha is x in kernel A. So now you have to show that alpha x is also in kernel A. So the question is alpha x in kernel A if x in kernel A So, well, to check A times alpha x, alright, and by the matrix multiplication, we can move alpha in front of A, and so this, and because x is in the kernel A, so AX is 0, and alpha 0 is also 0. Okay, so that we have done. Okay, and note that fourth question above the closure property So the people refer to this result as saying that the kernel A, this set is closed under vector addition. Okay. And the kernel A is closed under scalar multiplication. So this is another terminology to describe the same concept here. Okay, so I give five examples here. All right. So let's take 10 minutes break. Okay. And so we go back to our discussion at 11:10. So now, so our TA can distribute the graded over R for each. Okay, so the n-dimensional Euclidean space is also a vector space. Yeah. Okay. So please check. Home. All right. I will move on to give the definition. All right. So let X be a subset of a vector space or V. So now, suppose we have an underlying vector space called V, and now we consider a subset X of V. And this subset can be finite or infinite. A finite subset means that the number of elements in this set is finite. And we call a set is infinite. Set means that the number of elements in this set is infinite. Now, a linear combination of vectors in S is alpha 1 U1 plus alpha 2 U2 plus etc. plus alpha n Un for some vectors U1, U2, etc. Un in S and together alpha 1, alpha 2, up to alpha n. For some n. Okay? Equal to 1. So when we talk about, because the set can be infinite or finite, okay? So when it's very common, we refer to a linear combination of vectors in S. a linear combination of vector index. We mean that such a vector. Okay, such a vector. So we take U1, U2 up UN from S, the subset, and the scalars R1, R2, and form this sum. And the number of submains is n, and n can be arbitrary. Okay, can be arbitrary. But the point is that this sum is a finite sum. Anyway, even though the S, the set S itself is infinite, it can contain infinite many vectors. But when we construct a linear combination of vectors in X, we always pick up finite number of vectors in X, okay, to form this sum. So linear combination is actually a finite sum. Okay. And furthermore, the span of S denoted span of X is the set of all linear combinations of vectors. Before, when we talk about span of a set, this set usually is a finite set. But now we can deal with the span of an infinite set. Right? Infinite set. Right? So that the span, this is set, consists of all linear combination of vectors in S. And the linear combination is constructed in this way. Alright, so the first theorem. Okay. 2.4.b. So let X be a subset of a vector space. Be finite or infinite. Then span S is also a vector space. It's also a vector space itself with the same vector addition with the same vector addition plus and scalar multiplication. E with, okay. So the picture is that V is the vector space, and we may have a subset S here. Now the span, so this is span S here, right? So for any subset, when we create its span, then the span of X is also a vector space. And this vector space has vector addition and scalar multiplication from V. So it's inherent from V. Okay. Anyway. Any questions about the statement of theorem 2.4.B? So first of all, we have to verify that the vector addition and scalar multiplication in V still has causal property in the span. Okay, in this span. So you have to verify that. Okay, so proof. Vector addition from span of X, span of X, left to span of X. Okay, so we have U, V equal to U plus V. Alright, so we have to prove the claim that U plus V is in the span of X if U, V is in the span of. Okay, so we have to show the claim here. Alright, so now since U, V is in the span of X, they are U1, U2, UN, UN, right? And V1, V2 up to Vn in S, alpha 1, alpha 2 up to alpha n, beta 1, beta 2 up to beta n in R, such that U is written as alpha 1 U1 plus alpha 2 U2 plus alpha m UN. And the V is equal to beta 1 V1 plus beta 2 V2 plus beta n. Okay, so this is from definition. Because UV are in the span of S, so that U can be, it's actually this finite sum with this linear combination. Okay, so they are linear combinations of vectors in S. So now, when we add them together, then we find that the sum Alright, so you can see that it's also a linear combination of vectors in S. Right? So by the definition of linear combination. So this is so that U plus V is in S. Right? So we have done the claim. Okay? And of course I have to continue to verify that the scalar multiplication. Okay? It's causal property, but I will do that on Friday. So I stop here. And you can start the quizzes.